Hello and welcome to tutorial 21. Our topic today is lipids. Before we get started with that, just a quick reminder that the notes to accompany this tutorial video are available online through my website. And with that said, let's go ahead and get started. Lipids are naturally occurring molecules found in both plants and animals, and they serve a variety of different functions. Three of the main functions that they serve within animals is a source of energy storage. You're probably well aware of the fact that if you eat too much food, that some of that energy that's not readily needed by the body can be used and stored in the form of triglycerides, which reside in our fat cells. Lipids are also an integral component of our cell membranes, and we'll be talking about that in quite a bit more detail in the next tutorial, tutorial 22. And lipids also, some lipids, serve as chemical messengers in our bodies. All right, so what we're going to do is we're going to start out by looking at 5 different lipids. And these are all drawn in your notes on slide 2 for you as well. And we're going to take a look at, and let's do this in the blue pen in fact, we're going to take a look at the similarities that we see between all these structures. So what do all these lipids have in common? Well, first thing I want to point out is that I've drawn everything in line structure. And in case you have forgotten how to interpret a line structure, remember that all of the points, every point, represents a carbon. And remember that all the hydrogen that are bound to those carbons are just assumed. We don't write them in. It would take too much time. These are very large molecules, so they're just assumed for octet. All right? So hopefully when you're looking at these 5 different molecules, all lipids, you notice that they do have in common that they are almost all composed of just carbon and hydrogen. Okay, so I'm going to write that up here. Lipids are mostly composed of carbon and hydrogen. They are mostly just hydrocarbons. They contain very few polar bonds. I'm going to write that up here as well. And it's been a while since we talked about polar bonds. I think it was all the way back in tutorial 10 that we talked about bond polarity. So just really quickly, just a quick reminder that in order to figure out whether a bond is polar or nonpolar, we learned way back in tutorial 10 that we can calculate the change in electron negativity between the 2 atoms involved in the bond. And we can look up an electron negativity chart easily in any chemistry textbook. Any quick Google search will probably turn it up as well. So just a quick reminder that carbon-carbon bonds and carbon-hydrogen bonds are nonpolar. Okay, so we'll write that up here. So remember that carbon-carbon and carbon-hydrogen bonds are nonpolar. If we calculate the change in electron negativity for a carbon-carbon bond or a carbon-hydrogen bond, we will find that it is in the nonpolar range. They're in the nonpolar range. Now, if carbon or hydrogen is covalently bound to a highly electronegative atom, such as oxygen or nitrogen, well then the electron density is not going to be shared evenly between those 2 atoms. We're going to get partial positive and partial negative charge buildup. And we're going to find, if we calculate the change in electron negativity between those 2 atoms, that those bonds will lie in the polar range. Those will be polar bonds. So let's write up here, if carbon or hydrogen is bound to a highly electronegative atom, such as oxygen or nitrogen, I'll just write etc., the bond will be polar. Okay, so looking at all of these 5 structures, we see very, very few polar bonds. Okay, mostly it's carbon-carbon and carbon-hydrogen, which we already know are non-polar bonds. Look at cholesterol, you see just this OH here. So over here you do see 2 polar bonds for the carbon-oxygen, the oxygen to hydrogen bond. But the bulk of the molecule, all these carbons and hydrogens over here, non-polar bonds. So overall, lipids are non-polar molecules. And so they are going to be soluble in non-polar solvents. And they will be insoluble in polar solvents, such as water. Okay, so I'm going to write up here, overall, lipids are non-polar molecules. Okay. All right, so you might be thinking, well, yeah, we're talking about the similarities between these 5 molecules, but these molecules really look quite different from one another. The first 2 look very different from the second 2, and you would be right. So there are different categories of lipids, and we're going to talk about just three categories. We're going to talk in more detail about fatty acids. These first 2 molecules are fatty acids, a type of lipid called fatty acids. And these second 2, they look pretty similar to one another, but very, very different from the first 2. These are a category called sterols. We'll talk a little bit about those as well. And the last one that I have drawn here looks different than all the rest as well. This is called a triglyceride. We'll be talking about those as well. All right, so let's erase here and focus on fatty acids. Okay, fatty acids. Fatty acids will have a long hydrocarbon chain, sometimes referred to as the tail, attached to a carboxylic acid. Remember that this functional group is called a carboxylic acid. It has a carbonyl with an OH on one side, and that hydrogen will be acidic, so carboxylic acid. So let's write up here under fatty acids. Fatty acids have a long hydrocarbon tail. Put that in quotes because it's not really a scientific way to say it, but it kind of does look like a tail, attached to a carboxylic acid. Okay, and there are different types of fatty acids. You might already be familiar with saturated fatty acids versus unsaturated fatty acids. So let's talk about what those terms mean. Okay, so saturated fatty acids, that term, saturated, is referring to the hydrocarbon chain, that hydrocarbon tail. And just like a hydrocarbon that is saturated, when we say that a fatty acid is saturated, we're saying that the hydrocarbon tail is saturated with hydrogen. Remember from way back in tutorial 16 when we first talked about organic molecules and hydrocarbons, remember that that means that they contain, each carbon contains the maximum number of hydrogens possible because we only have carbon-carbon single bonds. So a saturated fatty acid contains carbon-carbon single bonds only. In the hydrocarbon tail. Okay, so obviously the two examples of fatty acids that we have drawn on slide 2, those are not saturated fatty acids. They do not contain just carbon-carbon single bonds. So let's draw an example of a saturated fatty acid. The easiest one to draw is lauric acid because it's only got 12 carbons, nice and short there. So let's draw lauric acid. So we've got a carboxylic acid and then 12 carbons. So 1, the carbonyl counts as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I always like to count just to make sure, count a second time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so this is lauric acid. It is the predominant fatty acid found in coconut oil. It is a great example of a saturated fatty acid. It contains only carbon-carbon single bonds. All right, unsaturated fatty acids. The hydrocarbon tail, the hydrocarbon chain of an unsaturated fatty acid is not saturated with hydrogen. It contains less than the maximum possible number of hydrogen because it contains carbon-carbon double bonds, one or more carbon-carbon double bonds. So it's right here. Unsaturated fatty acids contain one or more carbon-carbon double bond. Double bonds. And that, again, is in that hydrocarbon tail. So let's write in the hydrocarbon tail. Okay, and I say that because I don't want you to think that the carbonyl counts, okay, as a carbon-carbon double bond. It doesn't. It's a carbon-oxygen double bond. That doesn't make lauric acid, for example, that doesn't make it an unsaturated fatty acid. It's still saturated because the hydrocarbon chain is only carbon-carbon single bonds. All right, so unsaturated fatty acids can really be subcategorized even further as being monounsaturated or polyunsaturated fatty acids. So we're going to talk about those here. Put a little line. We've got monounsaturated fatty acids. And just as the name implies, mono means one. So a monounsaturated fatty acid would contain just one carbon-carbon double bond. And these carbon-carbon double bonds are always naturally, almost always naturally, of the cis geometry. Okay, so it's right here. Contain one carbon-carbon double bond. Okay, so as an example of a monounsaturated fatty acid, let's use oleic acid. It is an 18 carbon fatty acid with a double bond at the 9th carbon in the chain. So let's start over here because this is going to be a long chain, 18 carbons. So our carbonyl of our carboxylic acid counts as one of the carbons. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. We have a double bond of the cis geometry. So 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and that is oleic acid. Okay, and again, I always like to double check. If you're doing this on an exam, you want to double check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 carbons. That's how many we wanted with the unsaturation at the 9th position. All right, so then a polyunsaturated fatty acid, you probably already guessed, contains more than one carbon-carbon double bond. So let's write that here. Polyunsaturated fatty acids contain poly, meaning many, contain more than one carbon-carbon double bond. Okay, and I don't actually have to draw any examples down here because the two examples of fatty acids that we had drawn on slide 2 already happen to be polyunsaturated fatty acids. You'll see that the EPA contains 1, 2, 3, 4, 5 double bonds, all of the cis geometry, and the ALA contains 1, 2, 3 double bonds. So I'm going to go ahead and write one more thing down here before I forget, because it's really important. In nature, these are almost always of the cis geometry. Those double bonds will almost always have that cis geometry in nature. So in the foods that you eat, the natural foods that you eat, the fatty acids will have cis double bonds. Remember that means, if I draw a line here through this carbon-carbon double bond, remember that means that the larger two groups will be on the same side, making that C shape. The two smaller groups, you've got a hydrogen here and a hydrogen here, will be on the same side. The larger groups, so that carbon chain, will curve around in the cis, not the trans, geometry. Okay. One last thing I want to mention before we go on, and I didn't write this in the notes, but it's something that might interest you. You've probably heard of omega-3, omega-6, and omega-9 fatty acids as well. And omega-3 fatty acids are kind of all the rage right now because of their health benefits. So what does that mean? What is that referring to? Well, if we look at, let's just say this molecule right here and use it as our example, omega means the terminal carbon, the carbon farthest away from our carboxylic acid functional group. The one nearest is the alpha position. The one farthest away is the omega position. We can symbolize it with the omega symbol. And so in an omega-3 fatty acid, we're referring to a fatty acid that has the unsaturation, or the double bonds, starting 3 carbons from the omega position. So 1, 2, 3. So ALA is a good example of an omega-3 fatty acid. Okay. What about the EPA? Same thing. Here's our omega position. 1, 2, 3 positions from omega. That's where our unsaturation starts. So EPA is also an omega-3 fatty acid. Down here, okay, we're going to skip lauric acid because obviously it can't be an omega-3, 6, or 9 because it's not an unsaturated fatty acid. We don't have any unsaturation here. So we're going to go down to oleic acid. We've got the omega position, always the terminal, right here. So 1, 2, 3, 4, 5, 6, 7, 8, 9. We don't get to the unsaturation until the 9th carbon from the omega end. So oleic acid is an example of an omega-9 fatty acid. Now, I don't have an example of an omega-6 up here on the board, but hopefully you could see that that would just be a fatty acid that had the unsaturation starting from the 6th position, from omega. Okay, fatty acids in nature are actually part of larger molecules called triglycerides. And triglycerides form when the carboxylic acid from 3 fatty acid molecules connect to the alcohol functional group of a glycerol unit, creating 3 ester linkages. Okay, so that sounds pretty complicated. So let's take a look at that reaction simplified first. Okay, so we just said a carboxylic acid. So let's write a generic, or draw a generic carboxylic acid structure up here. I'll just write R for the rest of the molecule. It doesn't matter what it is. And I'll label that carboxylic acid. And it's going to react with an alcohol functional group. Okay, and I'm going to go ahead and draw in my lone pairs here. Label that alcohol. And again, it doesn't matter right now what the alcohol is, so just R for rest of the molecule. Could be methanol, ethanol, doesn't matter what it is. Okay, and just like I did when we talked about the glycosidic bond formation in carbohydrates, I'm not going to show you a mechanism here. You can certainly look up the mechanism in an introductory organic chemistry textbook or online. But what I am going to do is show one arrow just to show you what the new bond is that's forming. I think that that's very helpful for you remembering how to then draw the product. So I'm going to write an arrow here for my new bond forming, okay, between the oxygen of the alcohol and the carbonyl of the carboxylic acid. And we're going to lose the OH from the carboxylic acid and the H from the alcohol as H2O. So just to help you remember bonds that are forming, bonds that are breaking apart, and what do we get ultimately for our product. Okay, so we have a new bond now. This all stayed the same, so I just redrew that. That all stayed the same. We now have a new bond to the OR of the alcohol. I'll draw it over here on this side. And we lost H2O. Okay, and so hopefully you recognize this as an ester. Remember, when you have a carbonyl connected to an OR, so some other carbon chain over here, this is an ester. And I guess I'll write it in black here to be consistent with what I did before. Okay. Okay, that bond makes it an ester. This reaction, if you do it in the lab, requires an acid catalyst. So I'm going to go ahead and put that up there just for this generic reaction. But of course, in the body, reactions are catalyzed by enzymes. And so you won't see me writing that acid catalyst in the future when we start looking at the reaction for triglycerides. Now, this reaction is reversible. Water can split apart that ester bond and revert it back into the carboxylic acid and the alcohol. Remember that when water splits apart a bond, it's called a hydrolysis reaction. And just like hydrolysis of the glycosidic bond in carbohydrates is going to be relevant in digestion, the hydrolysis of the ester linkages in triglycerides is going to be important in the digestion of lipids, of the digestion of triglycerides. So a good reaction to just keep in mind, hydrolysis, splitting apart that bond with water. All right, so let's go ahead and take a look at this reaction in terms of the formation of a triglyceride from 3 fatty acid molecules. And I'm going to go ahead and put the alcohol first. The alcohol involved is called glycerol. That is the common name of this molecule. Okay, these are hydrogen. I'll go ahead and write those in. That was kind of sloppy. Okay, glycerol. The IUPAC name would be 1,2,3-propane triol. It's a triol. It's got 3 alcohol functional groups, 1 for each of the 3 fatty acids it's going to react with. And the 3 fatty acids need not be the same. They can be different. In fact, they usually are different. So I'll just write plus, and I'll just keep that part kind of generic. Just write R for the rest of the fatty acid chain, because it could be lauric acid, could be oleic acid, it could be anything. So we're just being kind of generic here still. And again, these need not be the same, so I'll put R prime here just to indicate that it's some different chain. And I'll put R double prime just to indicate that they're all different fatty acids. They can be the same, two could be the same, they could all be different. Okay. All right, so again, I'm going to just draw that arrow to help you remember what bond is forming. Okay. And it's going to happen with all three fatty acids forming a triglyceride. So 3 ester bonds will form. We're going to lose the OH and the H as water. And same thing here, the OH and the H as water. And the OH and the H as water, H2O. Okay. All right, so the result, a little bit more complicated looking than our generic reaction up there, because now we've got 3 esters that formed. Okay, so we've got an O, and let's keep that consistent, and I'll just do an R, an R prime, and an R double prime, and don't forget 3 H2Os. Okay, so here are the ester functional groups. 3 of them form. All right, and this is our general triglyceride. So I should label that triglyceride. And I should label our 3 fatty acids. Okay, so here's the general structure of a triglyceride. And again, remember that the fatty acid chains need not be identical. They can all be different. 2 could be the same and 1 could be different. And they can also be a combination of saturated or unsaturated fatty acids. All right, so we're getting a little busy up here, so let's go ahead and erase, and we're going to talk a little bit more about triglycerides, but we just need a little bit of room. So we're more familiar with the terms fats and oils with respect to triglycerides. So let's talk about fats and oils next. Fats are triglycerides that are solid at room temperature. Solid at room temperature. And fats usually come from animal sources. And they're solid at room temperature because they contain mostly saturated fatty acid chains. Okay, so it's right here, contain mostly saturated fatty acid chains. And those saturated fatty acids, because all of the carbon-carbon bonds are going to have the same molecular geometry, we're going to have all the same bond angles, 109.5 degree bond angles, they can stack together, they can nestle together more easily. And the closer those fatty acid chains are to one another, the stronger the intermolecular forces of attractions between them. And the intermolecular forces of attractions are going to be London dispersion forces, because we're talking about long hydrocarbon tails, nonpolar chains. Okay, so let's draw a picture of that up here. So let's use line structure just to make it easier for this part. Let's do lauric acid, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's do another lauric acid chain. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then let's make something different. Let's do stearic acid, which is a saturated fatty acid with 18 carbons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So what I'm trying to show here with this example is that these chains, these long hydrocarbon chains, can just stack together readily, increasing the intermolecular forces of attractions between those hydrocarbon chains, which are going to be London dispersion forces of attractions. And the stronger those intermolecular forces of attraction, the more energy it's going to take to break them apart. And so the melting point is going to be higher. And hence, that is why your fats are solid at room temperature. They're going to have higher melting points. All right, so things like butter, even coconut oil, that is one exception to the animal source here. If you keep coconut oil in your cupboard, you know that it's always going to be solid. That's because it's primarily just lauric acid, these 12 carbon saturated fatty acid chains. And again, they have the stronger intermolecular forces of attraction because they can stack close together. All right, so what about oils? So oils are triglycerides that are liquid at room temperature. So right away, you're probably thinking olive oil, canola oil, you keep probably all sorts of different oils readily available in your kitchen. So it's right here, triglycerides that are liquid at room temperature. And oils come primarily from plant sources. So I'll write here, usually from plant sources. And the reason that they have those lower melting points is because they contain more unsaturated fatty acids. And those unsaturated fatty acids have a little bend everywhere that there is a double bond. And so you'll find that the fatty acid chains will not stack together nicely in these oil molecules, in these triglycerides that contain more of the unsaturated fatty acids. They will not stack together as nicely. They will not nestle together. So those intermolecular forces of attraction will be weakened, which means that it will take less energy to start breaking them apart. So lower melting point. All right, so it's right here, contain more unsaturated fatty acid chains. Okay, that's going to be a little bit harder to draw, but I'll do my best here. Okay, so let's try to draw a triglyceride down here that has more of the unsaturated fatty acids. So it doesn't mean that they have to all be unsaturated. It just means that most of it is going to be unsaturated. So we'll still do a lauric acid here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, only because it's easy to draw. And then let's also add oleic acid. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we have our double bond. And now this is going to put, I'm going to try to be a little bit more, a little bit better about how this is going to look. It's going to put like a kink in the molecule. So 10, 11, 12, 13, 14, 15, 16, 17, 18. Let's do the same thing down here. And I'll do 2 kinks. So 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, so just drawing some other molecule down here. In fact, let's put more kinks in that one just to make it look more different. So 10, 11, 12, 13, 14, 15, 16, 17, 18. So I've just drawn 3 different chains. And so you can see that they're not necessarily going to stack and nestle together quite as easily as when we just had the saturated fatty acid chains, which all just had 109.5 degree bond angles that could fit nicely together. Here we've got some 109s, we've got 120s, so we've got different kinks in the molecules, in those fatty acid chains. So we have already said that unsaturated fatty acids naturally have double bonds of the cis geometry. But no doubt you have heard of trans fats in your foods. So where do these trans fats come from? How do they get into our foods? Trans fats come from a chemical process known as hydrogenation. The food industry takes oils like soybean oil and they hydrogenate those oils. So it's right up here. Come from the chemical process known as hydrogenation. Okay, I'm going to underline that because that means that the vast majority of the trans fats in our diet is coming from processed foods. So things like crackers, cookies, pancake mixes, notorious for having hydrogenated oils in the ingredients list. Even some of the lower quality peanut butters will use hydrogenated or partially hydrogenated oils. Pie crust, a lot of your prepared pie crust will have it. Almost all of your cake mixes will have it. So a lot of foods will have these hydrogenated oils where they take things like soybean oil or cottonseed oil or canola oil, doesn't matter what the source of the oil is, they'll take these oils which naturally have unsaturated fatty acids with double bonds of the cis geometry and they'll hydrogenate them. Okay, so let's take a look at that reaction. We actually did look at this reaction way back in tutorial 16, but let's look at it again with respect to a fatty acid chain in a triglyceride. So I've drawn just one fatty acid chain and you can see that it's an unsaturated, a polyunsaturated fatty acid that I chose to draw here, and this is also on slide 5 of your notes. Notice that I just wrote R for the rest of the triglycerides so that it wouldn't get too crowded up here. Okay. And when you hydrogenate those double bonds, you add hydrogen to them and saturate them, turning them into a saturated, that would turn this into a saturated fatty acid. If all the double bonds are fully hydrogenated, it should turn into a saturated fatty acid. Well, saturated fats we know aren't quite as good as the unsaturated fats, but that's not quite as bad as a trans fat. So where does a trans fat come from? Well, let's go to the blue pen here. Trans fats are a byproduct of the hydrogenation of oils. So I'm going to write here. And what happens is that not enough hydrogen is present to fully hydrogenate or fully saturate all of the double bonds in the molecule, but enough energy is present to break the double bond, and when they reform in the trans geometry. Okay, so let's write down here. A byproduct of this reaction is trans fatty acids. Okay, so we can imagine, let's say that two of these double bonds get hydrogenated, but maybe the third doesn't. And enough energy is supplied in the reaction to break the cis double bond, and it flips and reforms in the trans geometry. That's how trans fats get into our foods. Okay. So if you are trying to avoid eating trans fats, and you should, because you've probably heard about all the horrible impact that they have on our health. If you're trying to avoid eating these foods, you might think that you could just look at the nutrition label. If it says 0 grams trans fat, you're free and clear. You would be wrong. You have to dig deeper, because the food industry can claim 0 grams of trans fat so long as a serving has less than half a gram of trans fats. So there could still be a pretty significant quantity of trans fat in that food. So what you want to do is you want to look at the ingredients list. So I'm going to write down here, look at the ingredients. If you see the word hydrogenated in front of any type of oil, again, it doesn't matter what type of oil it is. It's often soybean oil, but it could be any other kind of oil as well, any kind of vegetable oil. If you see any kind of hydrogenated oil, and a lot of times it's partially hydrogenated oil. So I'm going to write that down here as well. Partially hydrogenated oil. And again, it doesn't matter what kind of oil it is. If it's been hydrogenated or partially hydrogenated, then that means that some byproduct of that reaction is bound to be trans fats. And that food, even if they're claiming 0 grams of trans fats, has some trans fats in it. It may be a very small quantity. It may be a pretty significant quantity. It's hard to tell at that point, because they don't have to claim it as long as it's less than half a gram per serving. And of course, who eats one serving? I know I don't. I eat several servings. So you can see how the quantity of trans fats could really start adding up in your foods if you're not being careful and trying to avoid those ingredients. All right, I'll leave you with one little bit of good news. You probably are aware that many countries have banned the use of trans fats in foods because they've been implemented in so many horrible health issues. And the United States is following closely. In 2018, the ban should be in effect, and hopefully we won't have to worry about trans fats in our foods any longer, and we can eat what we want freely. We are going to finish up our tutorial today by talking about sterols. And you'll notice that I don't actually have a slide dedicated to the discussion of sterols, and that is simply because I'm not going to say a whole lot about sterols. But you can turn back to slide 2, and you will notice that 2 of the examples that I gave for lipids were sterols. And I've drawn them up here, cholesterol and testosterone. So again, those are already drawn on slide 2 for you. All right, so one of the main things I like my students to understand about this category of lipids, about the sterols, is that they all share the 4 fused ring structure. Okay, so I'm going to draw the 4 fused rings. It's a 6-membered ring, followed by another 6-membered ring, followed by another 6-membered ring, and finally a 5-membered ring. Okay, so 6, 6, 6, and 5. And I had a very clever student once who said she remembered this by saying to herself, honeycomb, 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 house. Whatever helps you remember that general structure for a sterol. They're all going to have that in common. Now, the most abundant sterol in animals is cholesterol. And cholesterol is going to play a very important role in cell membranes, which is, remember, will be our discussion in tutorial 22. So we're going to be seeing sterols again in tutorial 22, specifically cholesterol. And cholesterol is also a starting material for the synthesis of other sterols that are needed in the body, including the bile acids, which aid in the digestion of lipids from our diet, and the steroid hormones, which include, but aren't limited to, all of our sex hormones, which include the androgens and the estrogens. So what I really want people to get out of this very short, very simple introduction to sterols is that structure. Remember that structure. Notice the 4 fused rings are going to have different things hanging off of them, and that's going to change the specific identity of the sterol. But as we run into sterols in future tutorials, hopefully you'll be able to recognize them right away because you will remember that 4 fused ring structure. All right. So we will conclude our tutorial 21, right here. And I hope that you will consider tuning into problem set 21 as well as tutorial 22, where we will go on and talk about lipids and their importance in the structure of cell membranes. Thank you very much.